No, it's actually
last speaker of the week is Yilei Chen from Visa Research. So Yilei has important contributions in obfuscation and in particular in cryptanalysis. And elegant constructions of matrix PRFs and constraint PRFs, and also vector tracing and obfuscation constructions.
All right, thanks.
Multilinear maps and
Thanks for the organizer and thanks for all the audience for coming the last day of the whole workshop. Not the whole workshop, but the first week of the workshop. So my name is Yilei, and today I'm going to talk about lattice, multilinear maps, obfuscation, and the possibility beyond. And it's a great honor for talking about all the topics where most of the inventor of these techniques are here. So I'd like to first thank these inventors and then the organizers. And so let's get started. So what are multilinear maps? So multilinear maps, so to talk about multilinear maps in cryptography, let me first start from the classical discrete log problem in cryptography. So the discrete log problem asks, so if I give you a generator G and G to the S for some secrets mod Q, could you find G? And if you conjecture finding S is hard, then they can show, first they show how to do key exchange, and then they say how to do public key encryption from this simple looking problem. And so after that, we start thinking about how to do something called bilinear pairing, so which looks like the following structure. So if you have the discrete log sample in two sort of source groups, and there's a magic way of computing the product of the exponent in what I denoted as the target group. So this is called a pairing operation. So you can think about the goal of this mapping is to still hide the secrets S1 and S2 in the exponents, but at the same time you're able to compute G to the S1, S2 in the target group. And the way of showing how to compute wave pairing in the bit curve group was dated back to 1986. And after many years, people find real crypto applications of it, including the last one, which is identity-based key exchange. So, cryptography didn't stop at bilinear maps, and one of the author of the bilinear map paper, Bonnet, and together with Alice Silverberg, they ask, so what if we have a more general way of doing mapping called multilinear maps? Say if we have a lot of source group, maybe they are the same, maybe they are different, and in each of the group, let's assume discrete log problem is hard, and still we have a magical way of computing the product of all the secrets in the exponent. So sort of think about the goal as the security goal, the functionality goal is what I defined, and think about the security goal as hiding all the exponents in the source group and also in the target group if it's not zero. So although they didn't find a concrete instantiation of this multilinear map, Bonnet and Silverberg proposed that if we have such a map, then there's a lot of cryptographic applications, including achieving unique signatures, broadcast encryption, etc., and etc. So for these three types of work, the first work has already won the Turing Award. The bilinear map applications has won the Golder Prize. And the third award we are waiting to see. And I can say, at least at this moment, this paper has already won the best paper award in my mind. And, and let me tell you why. So in this paper, oh, I haven't been to that one yet. Don't worry. So it's just Bonnie Silverberg. So although in the as I said in this paper they didn't mention any concrete instantiation, but in this paper they explore a lot of attempts of constructing such a map. And so here are two quotes from the paper. So first they say, if an M multilinear map is computable, it's reasonable to expect it to come from geometry, as the case for Wei and Tate pairing when n equals to 2. And then the paper lists a lot of attempts of searching for such a generalization in high degree let's call it high degree generalization of 8-bit curves. And this is, I think, in section 7.6, 7.4 or something like that. To say, after many attempts, if an n multilinear maps cannot be found for n bigger than 2, one could at least hope for such a map to arise from motives. So here, motives is actually double. It has two meanings. So one is like, first you are motivated by looking for such a map because of its cool cryptography applications. And on the other side, motive is also a mathematical term in algebraic geometry. So at the first time I read this paper, I think I spent half of the day looking for Wikipedia to try to understand what is a motive. And then I asked a lot of friends in the math department, and they try to convince me don't spend too much time on understanding what it is. And but at least we can say it gives us a lot of imagination. And even the original paper of Bonnet-Silverberg didn't find such a map. There's a recent proposal by Huang of computing trilinear maps from abelian varieties. So this one, I think right now the status is it still requires further investigations. Okay, so the focus of today is lattices, and this is a lattice workshop. And if I'm talking about motive, maybe the organizer will be unhappy. So why from lattices? So after the original proposal of looking for multilinear maps motivated in the paper of Bonnet-Silverberg, the first candidate instantiation of such a map actually come from lattice. It's a breakthrough at 2013 by Gagdentry-Halevi. So why do we think about this looks like a lattice-related candidate? Because this is actually a candidate based on a variant of the untrue problem. Let me just clarify here. By a variant of the untrue problem, I mean like the instantiation of the intuition of the harness come from a variant of the untrue problem. So the actual security, whatever you want to prove, cannot be based on whatever variant they have proposed. So no security reduction to any concrete assumption is given. And the paper is also beautiful. It lists a lot of cryptanalysis attempts of breaking their candidates. To be honest, I also watched the video of all the previous lattice talks and during the workshop. And I think at least you can learn half of the material from the previous talk by just reading this paper, section 7 or section 6, maybe I remember wrong. All right. So after the first, so I also want to say something about, so this paper actually gives a new way of thinking about multilinear maps. So the previous way we think about multilinear maps as a generalization of bilinear maps. So you have a source group, you have source group 1, source group 2, you have secrets hiding in the exponent, you try to compute it, and it will go to the target group. So this work gives a new way of thinking about multilinear map. You can think about it as a homomorphic encryption plus public zero test functionality. So homomorphic encryption, like the ideal version of it, allows you to compute unencrypted data on and on and on. And in the end, it's still encrypted. You need a secret key to be able to decrypt. And the multilinear map allows you to have additional public zero test functionality so that you can test whether in the end you get an encryption of 0 or encryption of non-zero, at least. Let's think about it in this way. So, and then, so throughout maybe the first half of this talk, you can think about the multilinear map I'm talking about today. The security goal is you can think about the minimum goal, and then you can think about the best goal. The minimum goal is to hide the exponent in the whatever way you compute until the last one you can test whether it's 0 or random. And the maximum goal is like the only thing you can do is to evaluate in the test. You cannot learn any partial information. And after this work, there's two other proposals of multilinear map candidates. Actually, each of them start from, I think it's fair to say they are starting from one of the previous lattice-based fully homomorphic encryption scheme. The one which we will call CLT13. It's based on a variant of the approximate GCD problem. And as we heard from yesterday, the best algorithm to solve it is a lattice algorithm. And the last candidate from GGH15 is another candidate inspired by the fully homomorphic encryption scheme from GSW13. So really, so far I have told you we have 3 candidate multilinear maps from lattice theory, and their candidate, and all the papers mention how do you do correctness, and they provide you what's the intuitive way of achieve security. And what really gives multilinear maps a punch is what can you do more than what is originally suggested in the Bonnier-Silverberg paper. So in fact, this is only the partial picture of what you can do from multilinear map, which is explored after 2013. And in the center of the picture, I believe it is this line. So how to construct indistinguishability obfuscation from multilinear maps.
Can you go back to the previous slide? So I/O, I don't think directly implies an maps, right?
Right. So you need to assume additional assumption like discrete log is hard and NISIC. This is work by one of the TCC papers, I think. So here, all the arrow means adding all the normal assumption you can make, not crazy assumption. This is the rough intuition. So I think in the center of the picture is the connection of multilinear map implies indistinguishability obfuscation, and then indistinguishability obfuscation implies everything. So let me say more words about indistinguishability obfuscation here. So indistinguishability obfuscation is a notion of obfuscation defined by the work of Barak et al. So what is a program obfuscator? So you take a clear text program, you try to compile it, and make it an obfuscated program so that no one can understand what's going on, besides the input-output functionality. And we want the correctness for the obfuscation to be that whatever you output as the obfuscated program, preserve all the functionality from the clear text program. And the security goal is, so for 2 programs which has the identical functionality, the obfuscation of program 0 is indistinguishable from the obfuscation of program 1 from the adversary's point of view. So, so really this picture should be reshaped. So right now I try to make the picture so that multilinear maps also imply most of the stuff. But really the land of cryptography after 2013 looks like this. So really it's indistinguishability obfuscation implies a lot of things. And usually we call it the big bang in crypto. And really the center of, take one step back. So let me take one step back on one of my personal experience. So at 2015, I come to the Simon's workshop as a crypto student. I think the first time I really understand how powerful is cryptography is by reading the paper of indistinguishability obfuscation imply everything, especially the paper of Sahai Waters. So this is a picture of actually on the whiteboard on the 3rd floor, I think, on this building in the summer 2015. I think me together with Oksana and the other students are reading the paper of Brent, constructing functional encryption from obfuscation. And as you can see, all the paper at that time from obfuscation looked like this. So you're puncturing at a lot of spots for the people who are familiar about the history. So really it changed the way that we think about how to construct a cryptographic application. It's sort of in the extreme sense, it tells you that this is something that you can do, and essentially everything you can do. And I'd also like to mention one of the application built from indistinguishability obfuscation without using puncturing. It's the work of Yamakawa et al. That shows how to construct self-bilinear maps from obfuscation plus something. So, so what is self-bilinear map? So previously, when I mentioned bilinear map, you think about there's 2 source group and you map to a target group. So self-bilinear map says the target group is the same as the source group. So you are not stopped by one mapping. So if you are mapping to the same group, then it means you can go on and on and on and on and all the way up. So Yamakawa et al. Shows like how to build a self-bilinear map from obfuscation in a very simple way. So think about you have just any group you like to work with for discrete log problem, but right now we are going to stuck with the RSA group. So think about you have a discrete log sample g to the s, and s is the secret component. So you have g to the s in maybe the RSA group, but you don't know how to compute the exponent, the elements in the exponent without revealing it. So here's one way to do it. You have something called a raised to s function, and you obfuscate it. So the obfuscated functionality is exactly you take any elements and then raise it to x, and you publish an obfuscated version of this code as part of the encoding for s. So it turns out intuitively the obfuscation should hide s, and indeed Yamakawa et al. Proves that when the n is a RSA modulus, morally that the obfuscation hides s, and it becomes a self-bilinear map. So I hope to show this example to you, like just to show like how powerful indistinguishable obfuscation is. And indeed, there's a lot to capture if we focus on this topic. So, oh please.
What can you do with self-bilinear map?
So I think the easiest answer is like you can have like a homomorphic encryption for unbounded degree for free. So that's the strongest application, I think. Yeah.
So in this encoding, how will you compute the map?
How do we compute the map? Right. So think about if you have g to the s1 and the obfuscation of raised to s1 functionality, and you have g to the s2 and the obfuscated raised to s2 functionality.
Oh yeah, yeah.
So you put that guy inside the here, and what the output is g to the s1 times s2.
One other question. So you don't have a zero test here.
So here you can think about really the target group is the normal the discrete log group you are familiar with. So g to the 0 is literally 1. Right?
Maybe I missed something with your previous reply. So you get g to the s1, s2, but how do you get the obfuscation of the raised to the s1, s2 problem?
Oh, great. So you also need to do that. So I think you can take these two functionality and multiply them together and obfuscate outside. Right. So right, there's a caveat. So in theory, actually, the wrap-up part becomes blow-up. So it's actually not, in theory, it's not, even in theory, it's not like unbounded. But I want to say, if you have a self-bilinear map, which even the size doesn't grow, then it's great. So great questions. So let's come back to obfuscation, and So I want to come back one step before, like say, so right now we have a rough link, say lattice theory can give you candidate multilinear maps, and the candidate multilinear maps gives you candidate program obfuscation for all the functionalities. And you can ask, where are we right now? So here is a rough picture of where are we right now. So again, this is like a selected picture of all the applications. So on this picture, we have all the applications name, and they're either with blue color or with orange color. So with the blue colors, I think about them as the applications inspired by multilinear map kind of way to design applications. And right now they have a reduction from LWE. So say if you can break these applications, you can break LWE. And the rest of the applications right now still they have candidates, and essentially because we still have I/O candidates. That's why everyone, you can start from I/O to build one. And also like someone, if you directly build it from multilinear maps, we don't know how to break it, and they are still very good candidate to study. And so here there's also additional support that if you think multilinear map is too complicated to analyze, there's even attempts to build indistinguishability obfuscation without using multilinear maps. I think I will mention like some of the future directions also related to the idea of without using multilinear maps and related to lattice to build I/O. And so many people are curious, like so what are the I/O candidates we have right now? So I try to make a slide summarizing the candidates' status of all the multilinear maps in I/O. And in fact, there's already 2 websites summarizing like the current status according to their opinion. And after making this slide for a week, I kind of give up. So this is a slide I made in 2016 at my early stage of PhD, where I talk about how to build a delegation RAM computation from I/O. And this is the current status at that time. I think now it's keep growing. So I think the purpose of this talk is not to make the status complex. We want to clarify what's the current status. So I hope to give a status report, a partial status report at the end of the talk that choose the clearest path that I can understand to the audience. But I think at least this is still an open problem. And so this is a summary of open problem left in the Simon's program summer 2015. And problem number 3, Amit is still there. I think this award is still not given out, right? Absolutely.
But I mean, is it at the same rate?
All right.
Inflation adjusted.
What?
I'm personally funding an increase to $1,000.
$1,000? Oh, I need to remake my slides then. Yeah. So $1,000 once, $1,000 twice. Deal. All right. Right. So this is the first open problem. I remind everybody, this is not what I invented, but yeah. All right. So. Yeah.
From here, problem 2 is now solved, and the others?
Yeah. So for problem 2, I double check with the organizer that he already paid the price.
So the others are still open, right?
The others. So some of them I'm not familiar about, so for example 8 and 4 I need to check with the experts. I also want to remind that actually 7 should still considered to be open because we're still trying to understand that proposal.
It just is plausibly hard.
Which one?
Right, so that's also we need to go to the lawyer to understand what the so plausibly how long does it stay and what's the possible to who, right? There's a lot of angle to look at it. So we need to re-audit all the open questions left from 5 years ago. Anyway, so the focus of today, I want to give you more insights on the explainable lattice theory behind the multilinear maps. As so essentially understand the lattice theory behind both GGH13 and the CLT13 are still fascinating open problems. I will remind you in the end. But today I will spend more time on the candidate of GGH15. In some sense, this is the only application, this is the only multilinear map which nowadays give us two or a few more provable applications that inspired by this way of designing cryptography applications. And the original paper is called Graph-Induced Multilinear Map from Lattices. And let me give you, before introducing GGH15, let me give you 2 reasons that I want to think about emphasizing it. So the first reason is what I said, this gives a way of designing application following almost the multilinear map approach and with a security reduction based on LWE. And in some sense, this also creates a new methodology of building lattice application after what we so-called GSW13 FHE and the BGG plus 14 AB scheme that we just heard from the previous talk. So I think if you have a way of designing application and it's used more than 3 times by other paper, we should consider this as a framework. And I think these are the 2 well-known frameworks that we have heard about during today and maybe in the last few years of development of lattice applications. So after saying that, let me start to the real business of the plan of today. I have finished introduction, the overview of lattice theory to multilinear maps. And for the most of the rest of the talk, I will talk about GGH15, its functionality, and the security overview. So I kind of separate part 2 and part 3 in the following logic. So in part 2, I will try to only explain the functionality and explain the security intuition by small example. So this small example doesn't come a big application. And then in the third part of the talk, I will try to instantiate these small examples in a large application and understand why is this secure, what goes wrong. And the open problems will be mentioned during the talk, as you see from the $1,000, and also later we will have more to come. So I'll try to cover all of them before 5. So, okay, so let's get started. So, during the preparation of the talk of this work, it reminds me of when you read the musical notes. Right? So, I don't know how to deliver the feeling, but the rough feeling is the following. So if you read the musical scores in the early age, so for example, like this one, so it turns out, aside from which keyboard to press and which musical instrument to use, it doesn't give you a lot of information about so how should I really play this? So should I play with this emotion, or should I play with this? Right. So I have the same feeling of reading actually all the 3 multilinear maps paper. So let me tell you the feeling of reading these 3 papers. So first they tell you what they are trying to do. And then they tell you how to achieve the correctness first. And then security is widely open. They will tell you what's the attempt they made and what are the attempts they have made and why they didn't work. And you learn a lot of stuff. So in some sense, they are great papers that they tell you how to do things correct, but how to interpret it and how to use them, it's all up to you. It's like when you see the musical score, you have your own interpretation of how to play with it. So I hope in this talk I can deliver such a feeling like I tell you the right pace of understanding this piece of work. Also, just to prepare the audience, in the original about the brief history of the early age of GGH15, so in the first paper, in the original work of GGH15, they provided the functionality of the encoding and also their cryptanalytic attempts and their candidate of multi-party key exchange and I/O. So what I'm going to talk about today about both the proof intuition and the attack intuition are coming from a few papers, mostly in the 2 years after the initial publication of GGH15, and I'm involved in some of it. So, later I will not mention the names, but really the talk is basically an essence of the ideas from these papers. So also it gives you, I would like to mention there's also a lot of different views and the motives of looking at GGH15. So the original paper of GGH15, they say, we have a different way of looking at the FHE of gentry high waters. And sort of like another way of looking at GGH15 is by the work of Almaty-Packard and Kapula Waters by showing, by motivated by showing a circular security counterexample. And then they have the need to design such a structure that things cancels out, that I will explain later. So also in some of my, the work I have involved, you can see about GGH15 as capturing 2 lattice-based PRF or a generalization of the Killian randomization. So today I will take the simplest approach. So our goal is just to chaining LW samples. So I explain GGH15 as a way to chain LW samples. So let's get started. And just to remind you of all the notations of learning with errors. So we have a public matrix, and we have a sample y equals to s times a plus noise. So think about the noise coming from small distributions. And so consider a very similar variant. So instead of publishing one sample of LWE, I just publish, sorry, it shouldn't be called one sample, but LW sample with one vector as the secret. So think about, throughout this talk, think about the secret as a square matrix. And you just choose random vectors in each row of the matrix. And essentially you can say this is as hard as the LW for one vector because of a hybrid argument. And also, throughout this talk, we think about we are using LWE with small secret. Again, this is shown to be as hard as normal LWE by this work.
And this is inherent, right? Like the smallness of, you need S to be small. This is inherent. There's
Right.
no way to get around that.
Right. For correctness. For correctness.
Because it will multiply with the error.
Right.
Yeah.
Thank you. All right. So, so after so many preparation, let's look at how do they really do the chaining of LW samples. So in some sense, a natural analogy of think about multilinear map in the lattice work is the following. So, so for the multilinear maps in the discrete log language, you can think about all of them are G to the S1, G to the S2. So the natural lattice analog is put the secret element into the LW secret. So think about right now you have like a public A matrix and LW sample with S1, LW sample with S2, etc., etc., LW sample with SK. So right now, great, you have so many independent samples, and what we are lack of is a way to put them together, like the way of computing the product of the LW secrets into the final term, like the LW sample, putting the product into the LW secret of the last sample. So how do we compute such a map in some sense without revealing all the secrets that we have in the middle? So again, the idea is to use the lattice trapdoor that was introduced this morning. We will use lattice trapdoor sampling to chain them together. So again, a brief recall of the functionality of lattice trapdoor sampling. So think about lattice trapdoor as a way of finding, so if you have a trapdoor of a wide matrix A, if you have this trapdoor, then you can solve all the SIS problem using this trapdoor. And given any image Y, you can find a short preimage vector D such that A times D equals to Y, and D is small. And in fact, we can sample D from a discrete Gaussian distribution, as we mentioned in volume. And also, I want to remind you that one representative of a trapdoor is a 4-rank short matrix in Z. So Z is, think about this T is a square matrix over the integer, and it's 4-rank, it's small, and A times T equals to 0 mod Q, then T will be a trapdoor for A. So this is helpful for thinking about from the calculus point of view. All right. So the real idea of GG shifting is the following. So right now I'm trying to explain the idea with think about multilinearity 2. We only try to take the product of two secrets. So let's think about we prepare LW samples under two different A matrices. I'm going to reuse one of them. Later I will reuse many of them, but right now for degree 2, let's reuse one of them. So right now you have two LW samples separately. So the question is how to connect them together. So I'm going to connect them together using a trapdoor sampling. Say I have two LW samples, S2, A2, E2. I want to sample a preimage called D2 under public matrix A1. So we'll have the relation A1 times D2 equals to this LW sample. And again, notice that A1 is also the public matrix for the previous LW sample. And so also just to make everything nice, I also prepare preimage sampling for the first sample. Let's say right now I start from A0. A0 doesn't have any LW sample affiliated with it. So let's think about D2 as the encoding of S2, and think about D1 as the encoding of S1. So then the next question is how do we show the correctness? So how do we show the functionality we want? So, so to evaluate, so recall the goal is to come up with something like the product of S shows up in the secret term of the LW sample. So what we do is the following. So I compute A0 times D1 times D2, and the goal is to show that this equals to S1 times S2 times A plus some noise. And this is why it happens. So let's go slowly to this correctness issue, because this is almost the most important slides of the talk. So the most important part is to understand the correctness. Yes.
So you say I publish, but you've not exactly defined. So is it like public parameters, public keys, how?
So later I will give everyone a name. So you guys, D is the encoding, A is the public parameter, sort of. So right now, so think about only the A0 is the public parameter, and all the Ds are the encoding for each of the secret terms. So let's first look at what's the result of A times D1 times D2. So let's go very slowly. So you have first do A0 times D1. This is the first LW sample, because this is built up by the Trapdoor Sampling. So right now we try to open with the next encoding. It becomes this SAD plus ED. And notice that E is the error term and D is a small preimage. So this is a relatively small, we think about it as the noise term. And then let's look at the first term and open it up again. So right now, really we use the fact that the A1 is used both as the LW public matrix and its trapdoor is used to chain into the next value. So A1 times D2 opens up to S2 times A2 plus E2, as we show here. Right. So then multiply S1 outside. And then let's open this part again. So right now, S1 times S2 times A2 becomes sort of the functionality we want to achieve. We want to achieve like the end result is the product of S times the public matrix A2 plus some noise. So here we use the fact that S is also coming from small, because S1 times the error term is also becomes a bigger error term. So after calculation, we have the functionality that A times D1 times D2 equals to sort of think about this part as the functionality term, and the rest are all small noise. So you need to set up the modulus Q and the noise bound so that this term is relatively small mod Q. And so in the usual LW terminology, multilinear map terminology, we think about all the Ds are the encodings, and A is the public parameter. And in some sense, you only need one public parameter, which is the A on the left to start with. All right. So all right, we'll come back to this equation later on. And so right now I want to also generalize this functionality. I want you to think about a typical evaluation pattern of GGH15 as we are trying to encode secrets that usually later we can take the subset product operation. So think about there are like maybe 2 n secrets. We have n levels. And here I skipped a lot of A in the middle. So this is A4 in the end. And there's like A3, A2, A1 here, A0 all the way to the left. I want to encode this secret in the way that later I can compute the subset product of this S times A. And the resulting encoding looks like this. It starts from A0 and have like a D11, D10 representing each of the secret terms, exactly using this general chaining lemma, like A I minus 1 times D equals to SI AI plus error. And we will just extend the previous example of length 2 to an example of length n. And here's the example where n equals to 4. Again, let's do try to do the evaluation and learn, get familiar with what's going on. So think about I want to evaluate on a point with 4 bits, like a 0, 1, 1, 0. So 0, 1, 1, 0 will just select the corresponding matrix as the encoding that I want to evaluate. So let's say in this example, the first bit is 0. So I choose D10 as the first matrix. And the second bit is 1. So I choose this one. So by evaluating on 0, 1, 1, 0, I'm thinking about I'm evaluating like A, D10, D2, 1, D3, 1, and D4, 0. So let's just open it up again like previously to see what's the functionality. So it's really like just repeating the previous small example. So you first the first chunk, and then the error pops out, when you put the error together with the rest of the de-encodings, it becomes the relatively big noise. And then really, like you just open and again, and the noise blows up, and as this goes up. So as long as you set the modulus Q to be relatively large, so that all the summation of the error term becomes relatively small, you still have the correctness. Like the final evaluation becomes the product of S times A and plus small noise. So I do want to remind you that actually the noise grows exponentially with the number of levels, and it will become a problem in the efficiency. And I also want to mention that all the multilinear maps, these three candidates, have been implemented, and actually the noise blow up is the main reason that they are not very practical. So I will come back to the practical problem in the end, but right now, let's think in the asymptotical way that you can set the parameter so that the noise grows relatively smaller than the modulus. All right, and you evaluate, and you get the subset product in the picture on the top. So far, let's say I give you a brief impression of getting the functionality of the GGH15 multilinear map. And so really what we have done is a way that we encode all the LW sample, and in the end we are able to evaluate to something that is the product of the secrets times a public matrix plus some noise. Right. And if you think in this way that recall the goal is to hide all the secrets, and in some sense, to use this GGH15 multilinear map to do useful applications, we must embed useful information on the secrets. Right. So, so later I will give examples. But really the security, so far I have explained the functionality. So record the security. So now I will start mentioning security. So record the security goal is to hide all the LW secrets during the evaluation. Let's say this is the minimum goal, roughly speaking. But the reality of whether we can hide them in general is complicated. It depends on the structure inside all the S terms that we use during the evaluation. So let me explain right now what the structure inside of the S term look like. Because previously I sort of gave you the impression all the S terms are just a random matrix. Every row has a random independent value. But I mentioned to build useful applications from this multilinear map, we must put non-uniform stuff inside the exponent to make it useful. So right now, let me give you a small example of how to embed a useful structure inside of the secret term. And still, intuitively, it's not it's not obviously wrong.
Question.
Yeah, please.
So for random SIDs, everything follows from random.
Right. Yeah. And this I will also explain. Yeah. But yeah. All right. So from now, I will try to use small examples to explain to you what are the smaller examples that we can prove that hiding is guaranteed by the LW assumption. And I will also give a small example to show you that in that small example, hiding is very unlikely to be guaranteed by LW assumption or any other assumption. So let me start with the first small toy example. So think about all the secret terms. Instead of being all independently random, I inject some permutation matrix structure inside it. Sorry, not permutation, matrix structure into it. So think about all the matrix as like a 2x2 matrix MIB, tensoring with a uniform independent random secret matrix. And you can see and I define if you evaluate, you will have the secret product in the end. So if the product in the end goes to O 0, then I will say that the entire functionality is 0. If there's any block inside of the final product which is non-zero, I will consider the final product to be non-zero as 1. So in this example, the example is designed such that if you evaluate 0, 0, so you will choose A0 times D10 times D20. And in this case, you will have this matrix times this matrix. And actually, the terms cancel out. The product is a 0 matrix. So the evaluation becomes 0. And all the rest, you can say at least one block is left. So the evaluation, we consider them as 1. So this is just a toy example to demonstrate one way of injecting minimally useful structure inside the secret terms of GGH15. And it's actually an open problem to prove whether this construction hides all the secret structure or not. So right now, I'm going to give you another toy example 2. For toy example 2, we can actually prove all the secrets are hidden by the GGH15 multilinear map. And let me tell you this proof strategy. So actually, I have no idea about music. I come from an electronic engineering background. So on this whiteboard, I'm going to use this symbol to represent that the trapdoor of this public matrix is not used. So what does it mean by that a trapdoor of this public matrix is not used? It means that you can use it as a real random public matrix, and assuming LWE with this public matrix is random. So here I want to mention another trivial generalization of decisional LWE. So decisional LWE with a normal square secret looks like follows. We assume the LW sample is indistinguishable from A together with uniform random. So you can easily show that if the secret matrix looks like a permutation matrix tensoring with a uniformly random secret, then the LW problem with this permutation tensored secret is still indistinguishable from random because it's just a shifting of random rows. So with this toolkit, we can start trying to prove that actually this construction hides all the secrets and also all the secrets inside of the permutation of the structures.
These different colors, like the green,
Yeah.
do they represent something? Or?
Oh, yeah, it's a very good question. Actually, I use different colors to represent a different independent secret. So these two are the same. These two are different. It's important to clarify. So otherwise, if all of them are the same, then the proof won't work. Yeah, the proof won't work. All right, thank you for mentioning it. So we will first trigger LW permutation LW on the first two matrices where the public matrix is grounded, so it's safe. Everyone can use it as a LW sample. So right now we have the pre-image sampling of essentially two independent random matrices. And right now we are going to trigger the GPV pre-image sampling lemma, which says, so if you are going to use trapdoor sampling to sample the pre-image of a uniformly random matrix, then you're fine. Because there's actually a way to produce the same bit distribution without using the trapdoor of the trapdoor of the A matrix. And actually, all the pre-image are from a Gaussian distribution. And this is indeed the discrete Gaussian. So with this toolkit, we can also move on. So right now, in the next step, we are going to turn off the trapdoor of A1 using the GPV lemma, because we have proven that you're essentially only sampling the pre-image of random images. So there's another way of producing the samples just using A1 matrix without a trapdoor, and sample this as a discrete Gaussian matrix. Finally, you evaluate to get the uniform output. So then, right now we have turned the trapdoor off for A1 matrix. So you can move on again using these two steps. First, using permutation LWE, and then using the GPV lemma to turn all the trapdoor off. As we can see right now on the picture, there's nothing related to the original LWE secrets. And this is the way we prove that all the secrets are hidden in the GGH15 encoding.
Yeah, but you will need to make sure that this U21 does not have to satisfy any other dependence, right?
Right. So it's, yeah.
Pre-image sampling will only work if it doesn't matter what you map to, because it doesn't need to satisfy any other dependence.
Yeah.
Right?
The output is, so I guess, let me rephrase Shweta's intuition from what we have seen. So let's suppose so let's give a recap why this proof works. So essentially all the image we have deal with, they are only uniform and independent and only appear here. So if one piece of U2 appears somewhere else, then you are problematic at least, in the least sense. Right. So I guess by this, it's a time to introduce an insecure example, because right now we are very comfortable with this secure example. And the word one.
Is it the case that the functionality is actually trivial?
Right.
Yes, okay.
And so the whole point is later I will show that even it looks trivial, there is a non-trivial way to use it.
Okay.
Let me just rephrase Leo's question, because in the beginning of this example, I actually cheat a little bit, because the 2 example 2, all the inputs evaluates to 1. Because in the end, essentially we are showing that all of them evaluates to random. It turns out all the 2 applications that can build safely on GGG15, they also have this feature from the beginning, but they both find non-trivial way to use it in an exciting way, let's say. Yeah. All right, so right now we are at, so now it's the time to show an easy insecure example. So this almost wrap up with the general security intuition of GGG15. So how do insecure example look like? So the simplest way I can think about explaining an insecure example is to think about, you're taking the product of 2 secrets where one secret is completely 0. So don't worry about why do we think about this case, but just think about simplicity. Say you're trying to encode a secret which is identical equal to 0. Then the encoding of 0 is very close to a trapdoor. Let's see why. So to encode LW sample where the secret is 0, essentially the 0 term zero out all the big public matrix part. And if you sample a preimage of it, essentially you're sampling a preimage of a small error term. So recall that the preimage of 0 is a full trapdoor. So the preimage of a small is almost a trapdoor. And under some cases, it can be turned to a full trapdoor. But right now, I just want to convince you that it already makes your life very hard, because so suppose you have a way to compute a times something equals to small, then because this a is going to be used as the public matrix for the next LW sample, so this puts the secret term of the next LW sample in danger. So at least this gives you a very harsh security warning sign that this is not something safe to do. And for the people who are familiar about the literature, this is the intuition behind the zeronizing tag. Like the encoding of 0 are usually very dangerous in all the multilinear map candidates. And this is one small example trying to illustrate that. And more explicitly, if you have like a S2 term equals to 0 in this example, the evaluation will give you only the small error term. So if the small error term is small in the end, then actually you can extract this expression over the integers. And once you have this equation over the integers, there's a lot of things you can do to attack the candidate. So in fact, the built-in equation over integer instead of mod q is behind the intuition of all the multilinear maps attack since the first work by Chen et al. With Damien. So right now I just want to describe the brief security intuition. Later I don't think I have time, but in theory, in the slides, there's a slide about the full attack. So right now I have given two brief example of one trivial, sort of trivial secure case, one sort of simple attack case. And I want to wrap up this part of the talk by put this GGG15 like idea into the general framework of lattice applications. So in my opinion, there are like three big categories of ways to build lattice applications. The first way is we can call it regular-like schemes, where you can think about the rule of the LW secret as the secret key for public encryption, for example. And A is just A. And where do you put the message? You put the message think about you using LW sample to mask the the message. And the next framework is dual regif. And I mean, the quintessential example is the BGG plus that everyone call it. So the difference from the first idea is like right now we use the lattice trapdoor as the sort of the mask secret key. And then you can derive other functional keys or identity keys in the different public matrices. So really, GGG15 gives us a new way of designing lattice application. The key difference from the two previous schemes is you also put the message or the functionality you want to hide into the LW secret. So intuitively, you know, it sounds great, but it will make your security analysis more complicated because in the previous two cases, usually the LW secret is innocent looking. It's either random or small random, that's it. But right now, the LW secret, you can put permutation matrices, other stuff inside it, so the analysis becomes more complicated. So, please.
So the GGH15 maps, all the applications that we get from it, can't you get the same ones using the GSW type encoding? Like,
So this, yeah.
applications that we only know how to get from
Both ways.
GGH15?
Both
No.
ways.
Yeah, so you can always switch between
No,
them.
no, no, both ways. Like, as in there are applications you can build with BGG Plus, but you can't, if you don't know how to build with this GGH15, and the other way around.
So actually, lockable obfuscation is the one application that we only know how to do from this
Yeah,
way.
that's true.
Right.
Actually, this is open problem number.
Yeah, it could be more that we don't yet know how to do.
Yep. Sure. Sure.
This is open problem number lambda, I think. Give more details about what's going on. So in the last half hour, I will try to mention applications. I think I will try to do a truncated version of it and try to spend more time on open problems. So, so in the application, I will just put the security intuition I mentioned before, one secure example and one insecure example into the two applications. The first one is a private constraint PIF. The other one is obfuscation in general. So let me start from a private constraint PIF. So the goal of maybe the next 15 minutes is try to explain one way to get a useful application that is provably secure from LWE, and it's also useful. Like not everyone, everything evaluates to random. The application is called private constraint PIF, and as you can see, there's a lot of objectives under these big names. So let me try to explain what is a private constraint PIF in 3 slides. This slide doesn't count. So first, let's start from a pseudorandom function. So a pseudorandom function is a function that, so you have oracle access to a function. You query an input, you get output. You query another input, you get another output. And then the goal is to say that if you only have oracle access to it, it's indistinguishable from a truly random function. You can think about it as an exponentially large truth table. Now let me explain constraint. So think about it, you start from a pseudorandom function and try to modify so you have a sort of a master secret key for the original PIF, and you want to have a way to derive a constraint key, a modified key, that change the functionality on some points. It doesn't have to be 1 point. You can change as large fraction as you want. And just think about the functionality. You can change it and sort of still preserving the function structure. And the most important word is the last word, privately. So you want to change the functionality, and then you're asked to hand out either the original key or the changed key. The goal is so that the adversary who gets the key cannot tell whether you get the original key or the constraint key. So think about it, you have changed a lot of things, they cover it. So, right, 3 slides. So what is the motive of looking at private constraint PIF? Sounds like a complicated notion. First, let me give you a very strong motivation of look at it, is if you can achieve 2-key secure private constraint PIF. So in the previous example, I say you are either given the private modified key or the original key. So right now I strengthen the security definition, say you can ask 2 keys. So say maybe like 2 keys, one for constraint C1, the other for constraint C2. And so you're either given the 2 constraint key or 2 other constraint key. So instead of 1, you get 2. So only if you get 2, you only need to get 2 to achieve full-fledged obfuscation. So let's see why. So the obfuscation will be just the constraint key for the constrained circuits, the circuit you are trying to obfuscate, and sort of preserving all the functionality circuit, like the original circuit. And how to compute an input on the function? Oh, sorry. So original means like you give the constraint key on not changing any point functionality, like preserving all the like think about all 1 or all 0, preserving everywhere. So you're given 2 keys, and this is the obfuscator. So how to evaluate? So you evaluate both keys on the same point, and you just compare the evaluation output. If they're the same, you know it's preserving functionality. If they are different, you know this is the functionality triggered by the circuit C. And the constraint hiding implies that the constraint, the modified point, is going to be covered by the constraint hiding property. In some sense, you hide the circuit you want to obfuscate. But I want to mention that we actually don't know how to prove the 2-key security from LWE. We only know how to prove 1-key security from LWE. But this is a convenient way to think about why private constraint PRF is useful. And even
You have candidates that you cannot break.
so I think I think 20 minutes later I will just say like obfuscation is basically constraint PRF with 2 keys, and you can take our construction and think about it as a candidate. All right. So if you only have 1 key, then this also implies reusable gobble circuits. I think I don't have time to talk about these applications. So the point is like even like it has a contrived name like private constraint PRF, you can already use it to do a lot of things. For example, all the applications listed on the board. So right now let me tell you how to construct it from lattices. This construction comes with 3 simple steps. So first, you want to do, as before, like 3 slides. First, you want to start with a lattice-based PRF, and then you want to embed a constraint into it. Third step, you want to do step 2 privately. So let me briefly mention the ideas behind each of the steps. So we start from a lattice-based PRF, which is the Banerjee Packard-Rosen construction. And then to embed a constraint, we need to have a way to translate all the circuits into a permutation branching program. And the Barrington theorem shows how to transform a locked up circuit into a branching program. And finally, GG15 allows you to cover all the modifications up and have a security reduction from LWE. So let me start from something that Chris don't have the time to talk about in the previous talks, about how to do a lattice-based PRF. Actually, I want to do this step slowly because I have an acute open problem from this. At least I don't know how to solve it. So, so how to use lattice to build just a PRF without a constraint hiding? So think about you have a lot of, you have 2n LW secrets, all of them are square and small. You have a public matrix A. And the evaluation of the PRF is simply taking all the subset products and then rounded by a small modulus. By rounding in this talk, let's think about the modulus Q. The big modulus Q is super large, exponentially large, and we're just gonna round it to 2. By round to 2, I mean if like the final result is smaller than Q over 2, we output 0. If the final result is bigger than Q over 2, we output 1. And sort of like we need Q to be exponentially large, because later we are going to inject a lot of noise inside it, and we are going to guarantee that the amount of the noise we inject is always exponentially small compared to the modulus. All right, so let's do it. So let me prove to you why this construction gives a PRF. And I'm going to do a proof by example for one input. which is my favorite input 0, 1, 1, 0. I'm going to show that, excuse me, I'm going to show that this evaluation is random, indistinguishable from random. So let's get started. So first, I try to inject an LW noise here. And because I used all the small secret terms, so adding a small secret here, a small noise here, the product together with this is still small. So I can inject a noise without changing the functionality, and in other words, only changing the functionality with negligible probability. So then let's trigger LW on the last block, make it a random sample. And then let's inject a noise again and again. Unfortunately, that's the end of the slides. So we get a random sample for that equation, so for that evaluation, and you can do it for many inputs. So here is not an open problem, but the exercise. So we use rounding in the end. So we take subset product and then round it. So the first is an exercise that shows that taking the matrix product without rounding does not give a PIF. All right, it's an exercise. So the next question is, I think at least I don't know how to solve it. So that's why I call it open problem. So prove or disprove that when the modulus Q that we use like in the middle of the computation. So previously I mentioned like we use Q as an exponentially large value. So what if we use Q, which is a polynomial? And right now you are free to choose whether the secret terms are small or large or uniform or whatever. Not whatever, by the way, like maybe uniformly small or uniformly large. And the prove or disprove that this construction is a PIF. The only difference from the previous construction is right now the Q is becoming from exponentially large value to a polynomially large value. I think this is a very cute problem to think about.
And is anything known about the in between? Like, so for Q exponential in NP, we know how to prove it.
Yeah.
And for poly, we don't. And what about in the middle, like super poly?
Right. So I think so there will be a threshold that the proof doesn't work. Let's take that as a threshold. I think after proof doesn't work, everything is open. I want to make this as a more explicit open problem by say Q as a polynomial. But essentially, even it's slightly small. Right. All right. So now we have complete step one. Let's think about how to embed a constraint.
So about the second open problem, if you start with LWR, just let's assume LWR is your polynomial modulus. And can you prove it under that assumption?
I don't think so.
Under that?
That's
That would imply a solution here as well.
So the Richard's question is like, so previously I showed a proof that assuming LWE, and you put noise, 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 noise. So the question is like, if you assume LWR with polynomial modulus is secure, can you have a proof?
Also the noise to modulus ratio, I mean everything is polynomial. I mean the error
Right.
that we have done, everything is polynomial. Either even that one.
That's also not clear, I think. So open problem 2.5, like if you can do it from there. I need to think about it, yeah.
The natural strategy is iterative, right? And that does matter in the original. One noise is polynomial.
But if you state it as an LW assumption, there is no noise in that, the statement of the assumption. So I'm not taking any steps. There is just steps, I can imagine that.
Then the number of bits you forget will increase over. I think that's my guess. Yes.
Yeah. Thanks for the discussion. Let me have a cup of water. So let's continue, like how to embed a constraint into this construction. So I think I'm gonna speed up. To embed a constraint, you need to convert the circuit into a permutation matrix branching program. And there's a quick example of how to convert an AND gate into a matrix branching program. So think about you have input wire 1, 2, 1, 2, and we trigger Barrington theorem and have a with 5 branching program. Let's do proof by example. 0 and a 0, you get 1. 0 and a 1, multiply, you get 1. 1 and a 0, you get 1. Oh, sorry, you get identity matrix. And finally, only 1 and a 1, you get something which is non-identity matrix. So, and then you can extend this to a log depth circuit to a polynomially long branching program. All right. So the most important step is the last step, that how to do step 2 privately. So to do that, we are going to embed the permutation branching program into the secret term of the LW sample. So think about it, start from the BPR PRF, and instead of each matrix as a uniformly random matrix from small distribution, you think about it as a permutation matrix tensoring a small random matrix, for example, as this. And then you wrap it up by the GGH15 encoding, and that's it. So the way to wrap up is like think about there's a lot of intermediate A matrix, A3, A2, A1, and A0, and do the pre-image sample to sample these two first, these two, and these two. So each of them represents the encoding of permutation matrix tensoring LW secret. This is the construction. And so how to prove that the branching program is hidden in the GGH15 encoding? We're going to apply our small example lemma that we learned from the last part. So recall the toy example we had before, like all the matrices are permutation matrices, and all the LW secrets are independent in each chunk. So then we just apply the same proof technique, go all the way to the left, using permutation LWE and GPV to close the trapdoor, go all the way from the right to the left. So you can do the same thing here. And essentially, the goal is to prove the real constraint PRF with all the matrices, all the permutation matrices inside the secret is indistinguishable from everything sample grounded, like the first thing without trapdoor, everything is Gaussian from over the integer. And just to ask Leo's last question, like why is it useful? Like essentially, we are still doing a PRF. So it turns out like to make it a useful way, essentially you need to think about, you already published a lot of outputs by evaluating the PRF on the original unconstrained key. So you get a lot of output already. So then you get the constraint key. We are going to prove that the constraint key is secure even given these a lot of inputs. So then you can compare pairwise. So you can think about this as a way of token-based obfuscation. You're not going to be able to evaluate on all the points, but on all the points you have queried before. So you can partially evaluate on a lot of points from the original function. So the takeaway from this private constraint PRF construction is it is safe to use GGH15 to encode permutation matrices and make it useful. So I want to give a list of, so actually like doing constraint PRF, you don't need to use GGH15. This is just one example you can do from GGH15. In fact, like the one from GGH15, it only works for branching program, which is NC1 circuits. And there's a way to do private constraint PRF for all polynomial size circuit from essentially the BGG plus technique. And I want to rephrase, re-raise the open problem mentioned by Shweta. So, or maybe rephrase, let's say. So is there a way to transform like the GGH15 based application with the dual Raghib based application? So in fact, we have one example from GGH15, which is a lockable obfuscation that we don't know how to do from other lattice-based application framework. And I think predicate encryption, we only know how to do it from BGG plus.
Yeah, predicate encryption, period. Yeah.
Predicate encryption.
Exactly.
Motivation because the parameters would be worse, right, if you do GGH15.
But this is implementable.
Why?
Because it is implemented. You have downloaded it and compile it.
I just want to remark that, I mean, this branching program representation, it makes things much worse, right? Because you take NC1 and you blow it to poly size branching program, and then you degrade the error polynomially at every step. So the parameters are going to be much, much worse.
So it depends on, for some program, it's natural to represent it as a branching program.
Yeah, for sure.
Yeah.
I'm just saying that for things like PE, it seems like even if you manage to do it, you'll end up with a scheme that supports smaller depth and has much worse parameters.
Right, but the question is, let's say you're willing to take that hit.
Yeah,
can you
then can you do
Even
it?
then it's an open question. There's just a, yeah.
Of theoretical interest.
Theoretical,
Yeah.
right.
Okay. So I want to use the last 10 minutes to go through obfuscation and open problems. So I choose to do a simple way. As I mentioned before, like you can think about obfuscation is basically private constraint PIF with two keys, one for the constraint C and the other one for O1. So actually, this is a rather historically incorrect way to view it. I must confess that the historical correct way to view it is private constraint PIF is almost like the original obfuscator translated into the GGH15 language, and you only output one branch. So instead of outputting a functional branch and a dummy branch to compare, you output one branch, and there's a way to prove it is secure. So from this point of view, let's look at like the GGH15 based obfuscator. You can think about one branch which is encoding all the non-identity permutation branching program, which represents the functionality. The other branch represents all identity. I'm gonna skip all the details about the further Killian randomization, scalars, etc. Just to want to give you a security intuition that why is it, first, why is it so hard to prove anything from it? And secondly, when a sufficient amount of evaluation of 0 is available, we can actually break the obfuscation scheme. So first, let me explain the easier one to explain, which is that why the proof strategy doesn't work. This is exactly captured by the intuition mentioned by Shweta like a half an hour ago. So when you have two chains of this GGH15 chain, so record the last matrix are all the same. Like in this example, it's all A2. So instead of proving like one guy is indistinguishable random, right now you have two correlated samples, this one and the one on the top. So these are two correlated random matrix, and we don't know how to come up with kind of like an analog of GPV to handle that. That's kind of the easiest way to explain why the current technique of proving anything is difficult. Right, so that's the next slide. Can claim to, when a sufficient amount of evaluation to 0 is available, we can actually break the obfuscation scheme. The simplest example I can give is quite complicated. Instead, let me give you the summary of the feature of the attack. So again, let's record the basic evaluation pattern. So if you have an evaluation which actually goes to small, you will have some terms which are like noisy small terms, and you can recover the exact terms over the integer, and you can do many things after you get such an example, such a sample. And this is actually like first found by the initial attack of Chen et al. It's actually over CLT13, and then we generalize it to GGH15. So I think the talk I want to mention now is a classical polynomial time attack. It works as long as, so first let's think about this is all 0 functionality. And the second, let's think about, after you transform a circuit into a branching program, the input has some repeated pattern. Like it's input of bit 1, input of bit 2, input of bit 1 again, input of bit 1 again, 2 again, 1, 2, 1, 2, 1, 2, 1, 2, let's say this. Actually 1, 2, 3, 4, 5, 6, 8. But let's say all the input only repeat for constant times, then we have a way to attack. That's the description of the final result.
So please, so previously also there was an attack, right?
Yeah.
So how is this one different?
Yeah. So in fact, let me just skip to the summary of the. So this is the summary of the I/O status I promised to give at the beginning of the talk. So I can only say I'm more familiar about all the candidates derived from the GGH15 technique, maybe a little bit more about GGH13. So these are almost like the main works about that reflects the current status of I/O. And I think Shweta is asking the second line, like you have a quantum attack to simple branching program. So I think right now, if we take the short summary, if you take the original GGH15 obfuscation candidate, or you take the one from CVW18, you make sure that all the input bits in the branching program repeat for super constant time, in fact for security parameter many times. And you also make sure that when you inject the noise into it, you inject the super polynomial and many noise, forget about efficiency. Then there's no attacks. We don't know any other attacks after you make these two safety measures.
So this repetitions, what does it depend on? It shouldn't depend on the input, right? What do you mean by branching program?
Right. So branching program repetition, think about it like the branching program have the input pattern. So the first input bit, it controls, for example, the first step, the third step, the fifth step. I want to say if all the input bits, it only controls constant steps, then the CVW attack can work. If you do with more than constant, then it blows up.
So is this something you can usually ensure? I mean, is there a way to take a generic branching program?
Just put identity.
So you can pad it with identity matrix. That's the easiest way to do it. But I'm not sure you can compile it anymore, like after you download the code. But anyway, like it's. And also to connect to the talk next week, even if you use a quantum algorithm, we don't know how to break it. In fact, right now there's not many quantum candidates for I/O which is surviving. So at this moment, I don't want to say I believe this is quantumly hard, because I actually have some insights of using quantum algorithm to do something non-trivial on it, but I don't know how to actually break it. But I think it's an interesting direction if you have time and also wants to try quantum algorithms on some lattice-based constructions.
So these two constructions that you have in the short summary, GTH15 and CVW18, how are they different?
So how are they different?
GTH15 is just the original construction.
Right. So you can think about them.
Broken, as long as you can ensure this.
Yeah.
It's not broken?
It's not broken. It's not broken by me. Maybe someone else has the idea to break it. So I don't put a lot of money on it. But I think it's very hard to break. That's.
So then what?
So you can think about.
How is the CVW construction
differ from that? Right. So I think it's fair to say that in general you can take all of them as the dialects of the original construction of Sanjam et al. So I think in CVW18 we introduced two main differences. One is like we make sure that the scalar, the scalar, whatever it means, the boundary scalar can actually be non-commutative, which make this part less easy to use. And the other step is we make sure you must repeat for super constant steps. In fact, security parameter many steps. In fact, like this is something to point out because in the implementation of GG15, the authors don't assume that you need to repeat. But of course, to compare it is the first problem. So that's the second thing. Right. All right. So I want to use.
There was an attempt to simplify GH15 obfuscation by removing repetitions. And that's broken because of the attack, yes?
So I think maybe you refer to the implementation in the CCS paper. Yeah.
Right.
So that's where they didn't realize you need to repeat, and actually it's you need to repeat. So where to play next? I think let me try to mention the most important ones about the open problems. The first obvious open problems is to handle all the things in the middle that we don't know how to break, we don't know how to prove. I think two promising examples are witness encryption and the general evasive function of skaters. I must skip a very interesting joke in this talk. Okay. So, and then I think a very interesting direction is to, if we want to prove anything related to obfuscation or anything we don't know how to prove, we need new hard problems without mod Q, because essentially we are going to get a lot of encodings which like a small mod Q. I want to mention one of the very interesting attempts it's actually not from any multilinear map to IO approach, but rather from like a bilinear maps plus LWE plus low degree PRG all the way to succinct FE all the way to IO, this approach. So in the recent work of Barak et al. And Chen et al., they propose the following assumption. So say you are given an LW sample as normal, as we normally did, and then we want to put the error into some other low degree functionality. So think about the Q as a degree 3 function, and it takes 3 inputs, each of them are a vector of dimension m, and you get, say, the capital N equals to m to the 1.-1 many of these polynomials. So in some sense, you get PRG-like stuff, which is low degree, and it operates on small stuff. It also outputs things which doesn't, which are not mod Q. So they say if you have such an assumption, in fact, they need a decisional assumption of it, and then plus bilinear map, you can go all the way to IO.
So I want to remark here that these polynomials are, I mean, you can view them as degree 3 polynomials over Z. You can equivalently view them as degree 2 polynomials over ZQ. So you're not actually getting rid of the ZQ.
So this is it depends on the way you view it, you are saying? Or?
Yes.
Yes.
You can rewrite these things so that it's high degree over the reals, but it's degree 2 over ZQ.
It's still degree 3 over ZQ. You're just doing variable substitution, right? You're substituting E for S for E, and then you still get degree 3.
I think you only get degree 2 because you have to ultimately evaluate it in the bilinear map. We can check offline, but as far as I know, it's degree 2 over ZQ. It's always MQ. It's MQ multivariate quadratic, but over ZQ instead of over R. That's the difference.
This formulation I just don't see, but maybe apply.
All right, so automatically it implies 2 open problems. The first problem is just to break it. And the open problem number 6 is if you cannot break it, so can you build IO or something else directly from it instead of go through the whole route? So another motivation is efficiency. In fact, I want to motivate us to look back into GGH13 and CLT13 from the efficiency perspective. Because, so I have mentioned that you can build private constraint PIF and lockable obfuscation using the GGH15 framework. I think you can translate these 2 constructions in the language of GGH13 and CLT13. The challenge is, can you prove them on a concrete assumption, like a variant of untrue or approximate GCD? I believe if this is doable, it will give new insights on the security understanding of these 2 multilinear maps, and also it's very likely to improve the efficiency. In some sense, if constraint PIF is so powerful, if you can make it small and efficient, it's great. And the last open problem, again, remind everybody, this becomes 1 more 0 after it. And also I want to remind problem number 7, that's lattice-based crypto beyond the lattice. So this is the end of my talk. Thanks everyone for coming.